Hi everyone, welcome to Modern Optimization Methods. I'm Qingna Li from Beijing Institute of Technology. Today we will introduce the last part of Chapter 2, the convergence. Now let's briefly introduce the main contents in this part. We will introduce the trust region strategy, which is one way to update the iteration, and we will also introduce global convergence and local convergence. Finally, we will introduce the convergence rate. Now, let's take a look at trust region strategy. So you may recall that in the previous lectures, we have introduced two ways to update the iteration. The first way is we use the line search update, which means that we first choose a direction pk like this, and then we choose a step length alpha k, then we walk along this direction and we move the step length alpha k, then we come to the next iteration. And now for the other strategy, which is trust region strategy, it moves like this. So firstly, we choose a trust region around the current iteration. Then within this trust region, I found a minimizer of a model function. Then we move to that minimizers directly. So this is called the trust region strategy. Now let's take a detailed look at the main idea of trust region strategy. So firstly, as we mentioned before, we need to approximate the functions around a trust region area. So for this trust region area, we approximate the function value by a model function pk. Notice here that we have a trust region delta here. It restricts that we cannot move outside the trust region. We can only search within the trust region. After we search to find a minimizer we denote as pk, then we can update our iterations. However, the next iteration may not be that acceptable, so we need to find some rules to check whether we will accept it or we deny it. Now, there is a key point in the trust region strategy, the model function. What is the model function? Recall that after we choose a trust region around the current iterate xk, we need an approximate function to approximate the function f. So this function will be called the model function. And ideally, this model function should behave very similar to the original function. However, meanwhile, it must be simpler than the original one. So a natural choice is we choose the model function as a quadratic function. So quadratic function, we are very familiar with that kind of function, and we hope that in a reasonable trust region area, this quadratic function will approximate the original one very well. And here, notice that this Hessian matrix BK, we can choose different ways to choose BK. For example, BK can be chosen as the Hessian of the current iteration, or we can choose the approximation of the Hessian matrix. Now, let's illustrate the trust region methods by a figure. So if you look at this figure here, we got several kinds of lines. So let's first take a look at this line. So the dotted curve here actually means the contours of function f. Okay, so which is a very strange shape actually. It's kind of valley here. And another curve here, it is actually the contours of model functions. Okay, so the central of this dotted circle is the current iterate xk, so we are standing at xk, and we try to move toward the minimizer of function f. So for trust region, we actually approximate this function f by this model function, alright? So around xk, you can see that the model function behave like this. So as the contours goes down, the function values decreases for the model function. So if we try to find the minimizer within this trust region area, then we can probably go down here to the next iteration. And if we set a bigger circle or a bigger trust region here, then based on the contours of model function, we can directly jump to the point here, because this direction leads to smaller function values of model function. Therefore, we can see that the trust region step is quite different from the line search strategy. And different trust region areas will provide you different directions. Alright, so the first direction is here, and if you set bigger circle, you jump here. Okay, so this is what we want to say about the figure. Now, next, let's think about the convergence of the algorithms. So recall that our numerical algorithms generate iterations from the starting point x0 until x1, then x2, and so on. So a natural question is whether the iterations generated by the algorithms converges or not. Okay, so this is the first fundamental question we have to ask. If it diverges, then there's no need to do this algorithm. So we hope that this sequence will converge. All right? Now, so what do we define the convergence mathematically? So there are two cases. The first case is that if the iteration xk reaches an optimal solution of a problem within finite iterations, then we call this algorithm converges. All right? The second case is that the iteration is infinite and this sequence have an accumulate point. If the accumulation point is an optimal solution of the problem, then we call this sequence also convergent. So these are two cases that we define for convergence. Now, a simple example is like this. If you generate the sequence 1/k like this, then definitely you can see that it converges to 0. And in this case, this sequence, we call it convergent. All right? So another point you have to pay attention to is that the accumulation point must be the optimal solution. All right? If it converges to other points, not optimal solution, we will not say that this algorithm converges. Now, after convergence, let's talk about local convergence and global convergence. The two definitions, they are different in the starting points. Okay? If for a sequence xk, the starting point can only be chosen within a neighborhood of x star, then we call this sequence local convergent. In contrast, if the feasible solution x0 can be chosen within the feasible region anywhere, then this sequence, we call it globally convergent. So you can see that for globally convergent sequence, we are more favorable to this sequence. However, if a sequence have local convergence properties, we probably have some restrictions on the choice of starting point. Okay? So we prefer the global convergence sequence, actually. However, in practice, we have to take a look at the real situations of the problem. Now, let's talk about the rate of convergence. Okay, so think about a sequence and it converges to some point. So whether it converges fast or slowly, so it depends on how fast this iteration runs to the accumulation point. Okay, if it runs very fast, then we can see that we got a fast convergence rate. So how do we measure this fast or slow in mathematical way? So we use some definition for limit points. Okay, so we use a ratio here to measure whether a sequence converges fast or not. This ratio actually measures the distance of next iteration to the accumulation point over the distance of the current iteration to the accumulation point. Okay, so if we take limit for k running to infinity, and we denote that this limit will be beta, this constant. Now, we have different definitions for different cases of beta. So for the first case, if this beta is between 0 and 1, then we say that this sequence is linearly convergent. Okay, so it means that this iteration actually runs to the accumulation fairly fast. Okay, not that very fast, but fairly fast. And if beta is 0, it means that the numerator here runs much faster to x star than the current iteration. So we call it superlinearly convergent. And finally, if this beta is 1, it means that the numerator and the denominator, they are favorably similar to each other. This means that this xk plus 1 runs to the accumulation point not as fast as xk. So we call this sublinearly convergent. All right? In this case, for the sublinearly convergent sequence, we actually see that convergence is not that good. All right? And we have some examples here to demonstrate the different case. Now, if this sequence is 1 over k squared, then we do the accumulation calculation and take the limit, then we get the limit is 1. So in this case, it is sublinearly convergent. And if xk is generated by 1 over 2 power k, in this case, we do the limit calculation and we can see that we got the limit to be 1/2, which is between 0 and 1. In this case, sk is actually a linearly convergent sequence. Now, for superlinear convergence rate, we have a special definition here. If we take a look at this ratio here, so the difference from the previous ratio is that we add a power p for the denominator. In this case, it actually means that xk plus 1 runs to x star much faster than the current iteration. It's even several times of the current iteration. All right? So in this case, we define the limit of this ratio as a beta. So if for p equals 2, we call this sequence quadratically convergent. For any p greater than or equal to 1, we call this sequence p-order convergent. Now, for an example, let's take a look at this xk sequence. So the sequence here is even more complicated than the previous two examples. We got 1 over 2 power of k, and we take limit, and we can see that if we choose p equals 2, then you can get the limit to be 1. In other words, we can see that this sequence is actually quadratically convergent. Alright, so we stop here and let's make a summary about this part. So in this part, we introduce the trans-region strategy, how we do the update. And then we introduce the convergence of algorithms, for example, how to define whether an iteration is convergent, and what is the global and local convergence, as well as different rates of convergence. Now, still up to here, we have finished the second chapter, and let's make a brief summary about chapter 2. In this chapter, we basically introduce some fundamentals for unconstrained optimization, including different kinds of minimizers, which is different ways of solution, and the optimality condition for unconstrained optimization. Finally, we also introduce line search and trans-region update for unconstrained optimization problems. Finally, we discussed different ways to verify the convergence of algorithms. Okay, so we stop here for this lecture, and see you next time.